This graph makes the Large Hadron Collider obsolete. The LHC was designed to solve the mystery of subatomic structure. This graph does that and much more. This graph proves that there is only one elementary quantum subatomic particle of matter, and that particle is the fundamental building block of the electron, proton, and neutron, ergo you, me, and everything in the universe. I've named this particle the half-life. All the subatomic particles of modern science are therefore not subatomic particles at all. They are simply debris. One of the best things about this graph is that anyone with a computer, an internet connection, and an Excel spreadsheet can duplicate this proof in a matter of hours, and it will always come out the same for everyone. Many years ago, while studying subatomic structure, I discovered an interesting fact. Well, it was interesting to me anyway. I discovered that if you subtract the mass of a proton from the mass of a neutron, the difference is very nearly exactly 2.5 times the mass of an electron. Well, that might have been significant, but then again, it might not. Several years later, researchers discovered a curious phenomenon. They discovered what has come to be known as the fractional quantum Hall effect. They discovered that in certain microcircuits, they were measuring electrical charges that were a fraction of the charge of an electron. Now, an electron is defined to be an elementary particle, and by definition, an elementary particle cannot be subdivided. So fractional charges are not possible. Vice versa. If fractional charges are being measured, then electrons are not elementary particles. They must be made of something smaller. So when I thought back to my earlier discovery about the difference in mass between the proton and neutron, it occurred to me, what if the difference was significant? What if there were a particle that was a fundamental building block of the electron, proton, and neutron? What if that particle was exactly half the mass of an electron? Of course, that begs the question, how do you prove it? If we lived in a perfect world, it would be easy to prove or disprove. In a perfect world, we would know the masses of all of the atoms, of all of the elements and their isotopes, exactly, to the nth degree. If we thought we had a factor of mass, we could just divide that factor into the masses of those atoms, and the result would always come out to be a whole number, or integer value, if it were a true factor. If, on the other hand, it were not a true factor, but just a random value, then we would get a random distribution of fractional remainders, and if those remainders were rounded down to one place of decimal, and the frequency of their occurrence were graphed, the graph would show just a random distribution across the range of decimal values between 0 and 1. So we would know for a fact that it was not a factor of mass. Well, we all know that we don't live in a perfect world. Well, the world may be perfect, but our understanding of it is far from perfect, as can be seen in any table listing atomic masses of elements and isotopes, where the uncertainty is blatantly stated. So even if we had found a true factor of mass, When we divide that factor into the mass data, we are most likely to always end up with a fractional remainder, not an integer value. So once again, the question remains, how do we prove it? Well, obviously, you will not give an integer value across the field of data by dividing that data by some factor. But if the mass data is accurate enough and precise enough, and if your factor of mass is accurate and precise, and is indeed a factor of mass, then graphing the frequency of occurrence in the range of decimal values between 0 and 1 of the fractional remainder rounded to one decimal place should show a tendency in that fractional remainder to gravitate toward the integer values at 0 and 1, with a distinctly diminished population near the middle range at 0.5. If the factor of mass is not a factor, but just a random value, then you should expect to see, once again, just a random distribution across the field with no discernible pattern. That is what this graph is all about. In this graph, because of the relatively small amount of data, the data has been arranged to show the deviation of the fractional remainder from its nearest integer value. For example, if a decimal remainder equals 0.1, then that remainder would be 0.1 away from its nearest integer value of 0. So a hit would be scored at 0.1. If, on the other hand, the decimal remainder were 0.9, then that remainder would be 0.1 away from its nearest integer value at 1. And once again, a hit would be scored at 0.1. The graph shows a high correlation to what would be expected for the results of a true factor of mass. The majority of the fractional remainders are observed on or near the value of 0 on the graph, the integer value. Nearly 60% are within 0.2 of the integer value, with a pronounced drop and a very low population in the middle region at 0.5, about 5%. By now I'm sure that everyone has noticed the obvious anomaly at 0.4. The population there is more than twice what it should be. At this point, we need to bear in mind some very pertinent facts. First of all, the mass of the electron is without a doubt the most accurately and precisely defined value known to science. No particle or unit of matter is as confidently recognized, as easily generated, or as easily measured as is the electron. And the electron has been generated and measured billions of times by millions of researchers around the world for centuries. So when we define a value to be half that of an electron, we can be just as confident of that unit's accuracy and precision. Now, observe what happens to this graph when we alter the value of our factor of mass, which here is exactly half the mass of an electron. If we increase the value of our factor of mass by just a very small amount, say add a 1 to the end, see what happens. The graph instantly randomizes. If we subtract the same amount, see what happens. Again, it instantly randomizes. Okay, suppose we add an even smaller amount instead, say 0, 1 to the end. Again, the form is disrupted. Subtract 0, 1 from the end. Same again. All right, let's take it another order of magnitude and see. Add 0, 0, 1 to the end. And subtract 0, 0, 1. It is only when we use the value of exactly half of the most accurately and precisely defined value known to man that we are able to produce this very compelling image. In light of what we have seen here, it might be reasonable to conclude that the apparent anomaly at 0.4 is the result of the introduction of some form of systematic or systemic error present in a particular group of data. If we map the elements of the periodic table where these 0.4 values originate, we find that over half of these values can be found in just 2 rows in the region defined as the transition metals, which includes the lanthanides. Since this is a relatively narrow region of a particular category of elements, and as such will all share some similar traits, this would seem to be a good place to start looking for the source of error. Secondly, if the fractional quantum Hall effect can produce fractional charges in microcircuits, then it should not be too far a stretch of the imagination to suggest that they are probably generated elsewhere as well. Of course, if it is a firmly held notion that fractional electrons and fractional charges are not possible, then when they are encountered by researchers, what will be the result? Naturally, they will be regarded as erroneous data and be summarily rejected and eliminated from the dataset. In all the literature I have found regarding mass spectrometry, the technique used to establish the atomic masses, it is always stated right up front that the ionic charge on the atoms under investigation are always assumed to be integer values. For example, +1, +2, -1, -2, etc. There is absolutely no consideration of anything else. So if fractional charges were present, since no one is looking for them, or even suspects that they could be present, those fractional charges could be corrupting the data, and no one would be any the wiser. We now have a brand new yardstick, a means to establish the masses of all of the atoms, of all of the elements and their isotopes, to the same accuracy and precision, and with the same confidence as we now do for that of the electron, because the mass of the electron is the starting point and the foundation. Since we can now know what the true mass of an isotope is ahead of time, it should be a relatively simple feat to track down and find the source of error. In short, this graph is indisputable and incontrovertible proof of the existence of a single fundamental quantum subatomic particle, and we have just entered a new era in scientific understanding.